Okay, so a good example of this is when you have the cosets of that are in modular arithmetic. Right. In this case, we don't use the operation times; we use the operation plus. So this example, let's say, if we take the coset, I think I said like 2 plus 5z. This is a coset in of the group G is z. Well, here let's say it this way: G equals z, and H equals 5z. And here's one coset, 2 plus 5z and 4 plus 5z are cosets. So if I take any element of 2 plus 5z and add to any element of 4 plus 5z, then I'll get an element in, well, I can do the 2 plus 4, which is 6 plus 5z. Now see, that's just an example. I can let's say it this way: it's in 2 plus 4 plus 5z. Right. So see, that's an example of this, but with the plus operation. So let's give another example, which is what I was saying here. That here's another example we can take. G can be the what you'd call a GL2, which is, I guess you do it this way. GL2, which is non-singular matrices, 2 by 2 non-singular matrices, and I'll say H is SL2. Okay, now instead of plus, I'm using the time operation. So let's say, well, I can have G1H, is still G, and G2H are cosets. Are cosets, okay. Now, if I take any element of G1H, let me copy this. And multiply by any element in G2H, I will get well, when I say any element, that means I'm going to choose a particular H, so that would be G1H1, and then that's times G2H2, which is equal to, I can just write all together without the parentheses, because matrix multiplication is associative.
And is that subscripts too?
These are all subscripts, yes.
No, at the top G equals GL. Is that a subscript?
Well, I guess you do use a subscript, right? Is that how? I don't remember how that works. I don't remember if it's parentheses or subscript, but it means non-singular matrices, non-singular 2 by 2 matrices. And these are the ones that have determinant 1. 2 by 2 matrices. Determinant 1. Okay. All right, so how does this show the principle? Well, let's see. The cosets. So from one of the exercises, so previous homework exercise says that two elements are in the same coset if they have the same determinant. Okay. All right. The same coset of H. Okay. All right, so let's consider the determinant. Let's consider the determinant of this. So, you know you can break up determinants. So I can write this as the product of determinants. Okay, I can write this product of determinant. How can I simplify that? Remember that H is the subgroup with determinant 1. So how can I simplify this? I mean, I can simplify this and this, because they're both in H.
And H equals a 2 by 2 matrix with determinant of 1.
Yes.
So determinant of G1 times 1. Determinant G2 times 1.
Right, so I can actually just take these two out. So this is just equal to this determinant of H1 becomes 1. And this determinant of H2 becomes 1. But I can simplify that even more. How can I simplify that even more? I can change that into a single determinant.
Well, that's determinant G1, G2.
Right. So what does that tell me? That tells me that that this and G1, G2 are in the same coset. They're in the same coset. And that's just what this picture says. This says that the coset of G1, G2 contains this element. Okay, so that's an example of normal subgroup. Okay. So I think those are two good examples to keep in mind, especially this example of the cosets of NZ in Z, because this is the basis of modular arithmetic. And the point that this chapter is trying to make is that when you're doing modular arithmetic, you really are doing this set addition. If I add 0 plus 2 mod 3, that means that basically I'm saying anything in this set plus anything in this set gives me something in the set 0 plus 2 plus 3z. Or if I take 1 plus 2 mod 3, that means I take anything in this set, add it to anything in this set, I'm going to get something in 0 mod 3, like this. So think about this coset addition the same way you think about modular addition. So this gives some example. Here it says, if I take one coset and add it to an element from another coset, I get a result in a single coset. So I can actually make a table of operations of sums of cosets. And it's just exactly the same as the table of modular addition. Actually, I'm not sure. I think that's a bad reference, but anyway. Okay. All right, and then you generalize this, not just for additive groups, but for multiplicative groups. All right, so we can do some exercises later on now. So here's some examples: rotation group and dihedral group and modular group. All right, so let's just briefly go over section 5. All right, so this is just an idea that now that we see that we can break groups down into smaller groups. If I have a subgroup, a normal subgroup of a group, then I can basically divide that group into two groups. I can consider that group as the normal subgroup and the group of cosets. The group of cosets is called a quotient group. So I'm basically factoring the group. So here's one example, okay. So suppose G is a group and N is a normal subgroup. Suppose further that N2 is a normal subgroup of N1. Then we can factor G into three groups, namely G mod N1, N1 over N2, and N2. Okay. Let's give an example here. Let's take an example of factoring groups. For instance, I could take Z mod 12, say. Now that has 12 elements, right? 0, has 12 elements. Now I could take every multiple of 3. Right? I could consider this set, I'll call it H, 0, 3, 3, 6, 9. Or let me do it this way. Let me consider H as 0, 2, 4, 6, 8, 10. Okay, as a subset of Z12. Right now, I claim that H is a subgroup of Z12. And you can show that by it's closed under addition. It's closed under modular addition. Right, if I take any two things in H, if I take any two even guys and I add them together mod 12, I'm still going to get an even guy.
Correct.
Yeah. So it's closed under modular addition and inverse. For instance, the inverse of 10 is 2. The inverse of 8 is 4. Okay. So H is a subgroup of Z12. All right, now is it normal? And the answer is, well, yes. There are two ways you can get it's normal. Any abelian subgroup is normal. And the other way you can get it is that H has, what's the index of H?
6.
Well, no, that's the number of elements. So what's the index?
Oh, the index.
Yes, the number of cosets.
Well, the number of cosets would be...
Or remember the formula we had up here.
It was the order of G.
Yes.
Over the order of H.
Yes.
Well, G has 12.
Yes,
So 2.
yes, so yes, since H has index.
And that goes
2.
with the proposition
Yeah.
that we used earlier.
Yeah. Also, H is abelian. Also, G is abelian.
And we can use the proposition that says let H be a subgroup of G with index 2.
Yes.
And then H is normal.
Yes, you could use that. Okay. So I can say, so what I have is I can say so, G, I can say it factors into G mod H and H. And G mod H is the G mod H, just to remind you, are the cosets of H. Now I can factor further. I can factor this way. I can say 0, 4, 8, which is contained in, which is a subset which is a subset of H, right? I don't know how to get rid of that. Let's do this. You have to fool it sometimes. Okay, so this is it's actually a subgroup. Let's call this, let's call it K. K is a subgroup of H. In fact, K is a normal subgroup of H. So that means that H factors into H mod K and K. So altogether, Z12 factors into Z12 mod H, H mod K, and K.
So if K is a normal subgroup of H, and H is normal to G, wouldn't K be normal inside of G as well?
Not necessarily.
Why not?
Because if you remember what normal means, it means that. So that's a good question. Let's do this. So here, let's just do this. So question: if K is normal in H and H is normal in G, is it always true that K is normal in G? And let's look at the picture. The picture is like this. Got a big G. So G is out here. And then inside of G, we have H, and then inside of H we have K. All right. So my big group outside is, this is G. And then this one is H. And then this one is K. All right, now, what does it mean that K is normal in H? That means that if I take, for instance, that means if I take an element here, if I take some element here, right?
Right.
And then I'll call that little h. Now, since K is normal in H, that means that K is normal means that H, K, H inverse equals K, or any H in H.
Right.
Right, now, what would it mean for K to be normal in G?
Well, H is normal in G, which means G, or no.
K is normal in G would mean that
G, big H, G inverse.
no, because if you, look, the only thing I'm
I'm
changing
sorry.
is the H to a G.
My bad.
I'm not changing the K. I'm only changing the H to a G.
So it'd be G and G inverse.
And this would be G and G inverse. And this would be for any G and G. Now, G, this little g, is something out here. This little g would be something out here. Right? Now, does this follow from this? Does the second one follow from the first one? And the answer is no, because this only talks about elements in big H. It doesn't say anything about elements in big G that are not in big H. It doesn't say anything.
So you can't prove that.
I should say that this does not necessarily follow. This doesn't necessarily follow from the previous statement. Okay, so it is not true that that K normal in H normal in G implies K normal in G. That's not true. I shouldn't say so because we haven't proven it yet. In fact, it's not true. It's not true. I mean, it's not. You can't prove it easily, and you can find counterexample.
Okay.
I can't think of a counterexample off the top of my head, but there are counterexamples. All right, now let me pick up on this a little more. Let's see if I can move this down. I don't know if it's going to let me do this. Let me do this. And then here we can do this. Why did it do that? I don't know. Well, I don't think it's going to work. No, it did not work. Let's try again. Success. This down here. I want to make some more commentary here. Whoops. Let's go to here. Okay. So that's down there. I want to make some more commentary here. Let's zoom back in. Okay. All right, now, what's the order of Z12 mod H? Now remember, H, that's the index. That's the number of cosets.
Well, that's 12 divided by 6.
So that's 2. And then we have the order of H divided by K. Let's see. I don't know if that's a student or I don't know. Well, I suppose I can answer. Hello? Hello? Yeah, hi. Sorry, I'm in the middle of a class. Sorry. Okay. All right, so H mod K is, so H had 6 elements, K had 3 elements.
So 6 divided by 3.
So that's 2, yes. And then here we have K, the order of K is 3. Now my claim, each one of these are groups. And they have no subgroups. No, I should say non-trivial subgroups. Do you see why they have no non-trivial subgroups? Each one of them, I mean, if I look at this group, there's no non-trivial subgroup of this group.
Well, because I want to say because you can't get back to the identity from it.
Well, I mean, a non-trivial subgroup would be a subset. That's a group. If you have 2 elements, there aren't many subsets. There's only one subset, which is the identity, which is the trivial subgroup. Well, how about K? Why does K have no non-trivial subgroups?
Well, because it's just itself. You can't break that down.
All right, but this actually relies on something we proved last week, which is if you have a group of prime order, there are no subgroups. Because every subgroup the order of every subgroup has to divide the order of the group.
Right.
So the only numbers that divide a prime number are the prime number in itself. Okay. I can say that because they all have prime order. Right, now let me do a different example. Okay, let's do a different example. So I'll start with Z12 again. Okay, let me start with something else. Let's start with, I'll use the letter H again, but here I'll do equals, I'll do this one, call this one let's see what I want to do here. 0, let me get this right. 0, 4, 8. No, that's not what I want. No, 0, 3, 6, 9. All right. Now H is also a subgroup of Z12. Right. Okay. And then what about Z12 mod H?
Well,
And it's also a normal subgroup. It's a normal subgroup because it's abelian. So what's the order of Z12 mod H?
3.
Okay. Right, we've got 3. Okay. Now let's consider a K equals 0.6. Then what's H mod K?
2.
2. Okay. And then we also have a K equal 2. Okay. Okay. So in this case, the sequence of orders, first we had is a 3, 2, 2. In this case, we have a sequence of orders 2, 2, 2, 3. Right? When we broke down Z12, it was 2, 2, 3. Here we have 3, 2, 2. The same numbers in different order. Okay. And in fact, this is true in general. This is actually called a kind of unique factorization theorem. Which is true in general. So the groups are not unique, but the orders are.
Is that part of a proposition? Or
Yeah,
a
that's
definition?
talked about here. It's the Jordan-Holder theorem.
Oh, okay.
Okay, so it's kind of it's a little bit complicated, so just a definition here: a simple group is a group that has no normal subgroups. Right. So in this case, we had so this one has it has no normal subgroups. And these also have no normal subgroups. So we've broken down a group into smaller groups that have no normal subgroups. And there's a name for this. It's called a something sequence, and I forget exactly what it's called. But it's called I'll have to look it up. But breaking a group down like this, you can always break a group down like this, and into a series of groups that have no normal subgroups. And it's a way of analyzing groups. Okay, well, let me stop here, and we can take a break, and then we can work on